Okay, thank you everybody for coming. So this week we're very happy to have Yikun Jiang give us a talk about it from ETH. So you can go ahead.
Yeah, thanks, Gabriel. Thanks for the invitation. Thanks for having me here. I will talk about a very long title. I'll explain everything, hopefully. The talk is mostly based on these four papers, especially my wonderful collaborator Hao is here. So if I can, any question I cannot answer, you might ask him. So um, let me just get started. So the ADS-CFT correspondence is a duality between a gravitational theory describing the geometries and a non-gravitational theory described by algebras. Especially, what do I mean? So we usually think of ADS as living in this box, and on the boundary there is this CFT where their gravity is turned off. So it's really a theory relating the uh, gravity in the bulk, which is describing geometry, and algebra on the boundary. So the natural question is actually we know a lot about ADS-CFT correspondence, but really, how does the macroscopic description of semi-classical geometry emerge from microscopic CFT data? That's a question I think it was addressed somehow, but still does not have a complete answer. Especially this map from microscopic algebraic data to macroscopic geometrical data seem to be hinting that there is a statistical mechanics mechanism behind the duality. There is a very important insight along these directions, which is the Takayanagi formula, relating something called entanglement entropy in the conformal field theory, which is I define, for example, this is a vacuum state. I define the reduced density matrix by tracing out a bar. I get something in A. I calculate von Neumann entropy, and it was shown to be related to area of minimal surfaces in ADS, especially given by this formula generalizing the Bekenstein-Hawking entropy. And I would say most of our understanding of the ADS-CFT correspondence come from already assuming the duality and then applying a semi-classical gravitational path integral. In this approach, CFT, the role of the CFT is playing is to fix boundary conditions for the gravitational path integral. What do I mean? Let me show you an example. This is a diagram figure coming from the Lundqvist-Maldacena paper proving the Rho-Takayanagi formula, where you say in CFT, you compute something which fix the boundary condition at infinity. Then in the bulk, you try to find smooth saddles going into the bulk. You evaluate the onshore action in the bulk, then that translates that back to the CFT quantity. This is the dictionary, GKPW dictionary, relating really like quantitatively realizing that proposal. But the more natural question is actually this assumed the duality to be true. But is there a way to actually see it directly emergent from the CFT without really assuming it? That's the first question. The second question is we have a lot of intuitions for holography coming from this analogy with tensor network. That's first pointed out by Swingle. Tensor networks are a way to represent quantum states in condensed matter systems. And there is this like a Mera tensor network where the entropy of these quantum states really come from counting the number of minimal number of cuts going in the extra direction. And a very famous model is this is the heavy code. But I would say a lot of the stuff we learned from these models are really toy models. So it's more like an analogy because we are not sure how is it related to CFT. We are also not sure how actual real gravity, like area, where is the area? The number of cuts probably is analogous to area, but really not quite. And we want to understand, is this structure really coming from some microscopic details of the CFT? Those are the questions. And I think in this talk, I will present answers towards these questions in the context of ADS3 CFT2 correspondence. The proposal is really there is a statistical mechanics mechanism behind it, behind emergence, which is the ensemble average over the universal BCFT data in the large C limit. I will explain what that means. And this averaging is really not so strange because it's just a generalization of the very common like eigenstate thermalization hypothesis. So we give it a name, it from ETH. Geometry is coming from ETH type behavior, which is described by this formula. I'll explain in detail. Now, I will also address the point, what actually is a holographic tensor network? Our proposal is as follows. So really, the structures we see in holographic tensor networks, at least in 83 CFT2, seem to come from the following procedure. You first discretize your CFT path integral. Then there are some CFT data associated to that. Then you perform the average over the universal data. And when you do these two steps, you will see gravitational path integral automatically pop out, and you can use it to prove the RT formula. and making it not a toy model. It really faithfully represent the holographic duality.
I can ask a
So,
question
yeah,
to so, this formula for the ETH, that's true in general dimensions, right? Or thought
yes,
to be
yes, yes,
true in general dimensions.
yes, yes, yes.
So,
Yeah, I'll explain what's special in 2D actually.
okay, but is the general belief that in general dimensions, I mean, in general dimensions, would you propose there's also an ensemble average over boundary CFT data that would produce, say, the gravitational part of the bulk?
Yeah, very good question. I cannot say for sure it works because in there is a very natural reason because in higher dimensions in 2D everything almost everything is controlled by OP coefficients, right? Because um yeah, I'll cut the manifold open. So actually using the state operator correspondence, OP coefficients seems to be enough. But in higher dimensions, you have those higher dimensional defects. You also need information about those. So I think OP, like some information about OP coefficient might not be enough. And I'm not sure if you include the other ones, whether that's enough or not. And there are some
I
special
see, I
features
see,
in 2D later. Yeah. Yes.
I see. You
It's,
know,
I think
no,
it's a
need to know
very
about.
interesting question. I don't know the answer.
Okay, sure.
Yes, yes. So let me first give you an outline. So first of all, I will first explain the stuff in CFT, which does not have a boundary. So I will describe how two-sided and multi-boundaries black holes actually arise from some averaging procedure in 2D CFT. And that actually yeah, will set up the stage and we'll see how root Takayanagi formula can be derived for these states. Then we will move on to discuss how actually to incorporate brains in the story from BCFT. And from that, we'll be able to give a new derivation of the multi-interval root Takayanagi formula for the vacuum state. Surprisingly, that's not related to black holes, but still give you these the entropies of these states. Then I'll explain why that's a holographic tensor network coming from what we call BCFT Legos. Next, I will explain how that's related to replica wormholes in the context of black hole information paradox. Finally, I will conclude. Great. So let's first start from the simplest example, which is just a two-sided black hole. Especially, I will show you, actually, it's a very, if you think a little bit, that's actually a very natural thing to do. And it's actually generalized. So so let me just first give more details into this two-sided story. So two-sided states, we describe it, the dual is described by the thermal double state in CFT. And we will see some statistical averaging procedure actually give you everything you want to know for the two-sided black holes, including the partition function, geometry, and the entanglement entropy. So this state is prepared by a CFT passing integral on cylinder. So if you do a passing on the cylinder, on the two ends, you get a quantum state, which actually can explicitly write down like this. So this is the cylinder Euclidean evolution. You get two states on the two sides. Um, this is yeah, A is a complete basis of the quantum states living on these circles. Let's first consider norm of this state. So the norm, you just give a bra and a cat, and they are also normal states. So you just give this number to square, which give you this expression. Now, instead of using energy eigenstates, I know in 2D CFT, you can organize using conformal families. The primary is descendants, and the descendants will combine into something called conformal block, especially in this case, it's a character. So you can write this as a sum over primary states of the character squared. So this is the answer. Um, and really, this expression is different for different CFTs. And you need to know all the spectrum, the primary operators in this theory to do the computation. But the idea is really holographic CFTs are some very special CFTs where the spectrum look very dense, actually. This is probably is the microscopic spectrum of that theory, where you see discrete spectrum. However, they are very, very dense. So in order to compute it, we can actually do some tiny statistical coarse-graining. It's very similar to what you do in StatMech. You just replace this discrete distribution by some continuous distribution. And then the answer will be the approximate coarse-grain answer. And actually, we're very used to it. Let's just do this computation. The averaging in this case, in the high temperature phase, is very simple because I have this expression. What you want to do is to say, I ignore the fact that the spectrum is discrete. I replace it by continuous spectrum. And the density, so I only need the density of those states and the range, of course. So the proposal is that for heavy states, actually the spectrum is given by the so-called Carty formula, which is just this rho zero factor. And I include all the states above the so-called black hole threshold. So you just smear the spectrum and you get this expression. So this is the average answer. And this is the character, by the way. If you're not familiar, that's fine. It's just a function. And so this is the proposal for the average, the CFT norm. And now we will show that actually it has a very natural connection to the Liouville CFT with ZZ boundary conditions. That's first discussed from my paper with Wan Zhen. And then also from that, actually you can see there is a gravitational path integral on the BDZ black hole from the so-called wormhole slicing, or really just the hyperbolic slicing. So let's just do it. So the first step, I want to connect these two objects, the first equality. The idea is, let me first explain a little bit what Liouville theory means, because you need to suddenly talk about Liouville theory. Liouville theory is a theory describing hyperbolic solutions in 2D. So 2D, the hyperbolic solutions can be written like this. So any metric is conformally flat. So the information of the metric can be packaged into a field. This is the Liouville field.
You can,
yeah.
Before you go on, can you go back just one slide just to make sure I understand something?
Sure.
So here, did you put in rho naught by hand or?
Yes, I do. Yes.
State?
I
Okay.
claim the claim is the average spectrum is rho zero, given by 0, 0, 0.
Okay, but you're gonna put the Carty there. You're gonna.
Yes,
I mean,
I'm calling the Cartan. Yes.
But there's no. I'm just trying to understand because maybe I'm mixing up with some calculations I know from before. Here, you're not doing any modular transform or anything like that. You just.
Yeah, very good question. The fact that I put Carty there is determined by modular transform.
All right. So you're using modular invariance. You're saying this is standard CFT thing, and you want to derive. So I should make sure I understand the difference from the usual paradigm. Usually, we say the term of is due to a bulk, two-sided eternal black hole, using ADS CFT, and here you want to derive that. Is that it?
Yeah, more or less, yes. Because let me tell you one thing. Yeah, as you point out. So the Carty formula is derived for the high temperature regime, for the extremely high energy regime. So it actually doesn't apply all the way down to the threshold. It's probably like start from here or something like that. The proposal is really in 2D CFT because of this paper by Hartmann, Keller, and Stoica. The proposal is I can extend this regime down to the threshold. And the average procedure is using this formula all the way down to the threshold and compute something.
I see. Okay. Yeah, because otherwise you would have been able to do this for any CFT. You would have been able to put in the Carty density at high energies.
Yes, but
for any CFT. Okay.
Yes. Yeah.
Here.
So yeah, actually, yeah. You will see actually for this, because we're so used to it, it doesn't seem to be very surprising, or maybe it's more or less trivial. But when you talk about more general cases like OP coefficients, actually you do see it is generalizing this idea. So I want to first rephrase this a little bit. Yeah, thanks. So Liouville theory is a theory describing 2D hyperbolic solutions. So when I write the metric like this, how does this give you a 2D hyperbolic solution? You want to look for solutions of the Liouville equation for this phi field like this. And we want to look at manifolds with boundaries. So there's a very special boundary condition called ZZ boundary condition described by the Tuzam-Lojkov. This is more or less speaking the boundary condition at infinity. So instead of giving you the definition, let me just show you the solutions with these boundary conditions. Actually, these are very, both of them should be very familiar for you. The first one is if you have only one boundary, if you impose the ZZ boundary condition, then this gives you the solution on the upper half plane. Or if you like to conformally map it, it gives you the solution in the hyperbolic disk. So you see from this expression, this boundary condition is the boundary condition imposed at imaginary z equal to 0. So it is this real line. It is giving a divergent factor. Okay, that's why I say it's at infinity. Another example, which is the one we are focusing here, two boundaries, you get a hyperbolic cylinder. So the metric look like this. The two boundaries are defined at imaginary z at 0 and also beta. So for these two values, you also see it's 1 over imaginary value of z when they approach the value, it becomes 0. So it's also giving a divergent factor. And this boundary condition is describing the behavior of the Liouville field are near these infinities, these divergent positions. So we are focused on this one. So how to compute it? So the idea is, I actually struggle a little bit. I decided not to show you the equations, but the idea is really how to compute this cylinder path integral
Go
with two
on.
boundary conditions. Yeah, sorry.
Just to make sure, we don't see any cursor. Are you actually using your cursor to point? Because I just want to double check that we're
Yeah,
not having a.
yeah, I am actually. So let me maybe if I want to use, I would just write it. What about this?
Okay, I was gonna say that before you do that stuff, like we
Huh?
don't see any cursors. Like
Yes,
we
yes,
just
yes, yes.
see. I make sure
Yeah, I
make
am
sure you know
using it.
that
I don't know what. Uh-huh.
when you say this
What
and
about?
this, like I think maybe it sounds like you're using the cursor, but we didn't
I
see
see.
it.
Okay, I would just point out that for that.
Yeah.
Yeah. So
Go ahead, sorry.
I will evaluate this path integral. It's a cylinder path integral with two boundary conditions. These red circles give you this. I impose these boundary conditions. So how do you evaluate it? I will use this point of view. You can directly evaluate ZZ propagate to the other ZZ. But a more general way to do it is by saying I first prepare the path integral using the cylinder with some without imposing a boundary condition. So it leave you some open cuts. It's give you the thermal field double state in the Liouville theory. Then I take overlap with the ZZ boundary condition, the ZZ boundary state. So that's just a different way of looking at this path integral. When you do that, actually that gave you this whole path integral because now I use the state to close this path integral. And the ZZ boundary state, the only thing you need to know is actually each ZZ boundary state give you a square root row factor. So that's actually why when you take the overlap with it, you get this row zero factor. Okay. And this is precisely what we get. So we show that the average answer actually is the Liouville partition function on a cylinder with two ZZ boundary conditions. You can actually show this more explicitly, but this is one way of seeing it. And actually, we will see that this is a very general mechanism for multi-boundary ones. So let me erase it. Now, so let's we show the first equation, this equation, these two are the same. Now let's show how they relate to gravity by connecting the second and third one. The idea is whenever you have a Liouville solution, the equation to solution to Liouville equation, you can put in this so-called hyperbolic slicing, which is yeah, just this 3D metric. Now, if you plug in a solution for the Liouville equation, this metric automatically solves the 3D Einstein equation. These solutions are nowadays very popular because they are related to so-called Mauthausen-Mouse wormhole. For example, I'm showing you an example for a genus 2 example. If you find the Liouville solution to Liouville equation on genus 2 manifold, you plug it in, you get this wormhole type solution in 3D. And this guy has two boundaries. One of them is at tau goes to minus infinity. The other one is at tau goes to plus infinity. So it's really a wormhole, a space-time wormhole. And first of all, you can plug this solution, the equation solution to this equation into the 3D Einstein-Hilbert action. And first of all, you will see on shell, if you do some computation that's first shown in this Chandra Collier Hartman Maloney paper, this gives you two copies of Liouville partition function on this 2D manifold. And the finite C answer actually, this is not only true on shell, but you can use arguments given in this Virasoro TQFT paper to say actually it's true even at finite C quantum mechanically. So the gravity path integral is the Liouville path integral square. Okay, that's true at finite C. That's an exact statement. So that's how actually these two are related. And now let's instead of considering these higher genus manifolds, we consider the manifold with ZZ boundaries. So what's special in this case? The ZZ boundaries do has a very magical effect. It actually glue the two 3D boundaries. Like here, there are two boundaries, but if the manifold 2D manifold itself has a boundary, if you plug in that ansatz, they will be glued together. What do I mean? Let me show you more explicitly. So for the previous case, it's a hyperbolic cylinder. if you plug in this ansatz, you will see this is precisely the solution of BTZ black hole, which is a solid torus, actually. So there are no two boundaries, only one boundary. And the fact what's really happening is that for these two cylinders, so just imagine like on the right hand side, on the bottom there is this gray surface. Gray surface is a cylinder, and the boundaries of the gray cylinders, these two red circles, I should probably change the color, are now represented by these blue curves. And when you plug in that ansatz, actually, all these blue curves at different tau slices here will be glued together. And that's why you get a one boundary solution. So let me just explain a little bit better. So the
Can I ask
CFT
a question
norm,
here?
yeah.
There's something that looks like when you go back maybe 2 slides, when you look at the expression for the norm. Yeah.
Yeah.
So when you score, the first expression looks something almost familiar, which is that you want to put a resolution of identity in between the bra and the ket. That's how you normally evaluate the norm. But it seems like your ZZ ket bras, it looks like a resolution of identity that glues together.
It's
Like
not. It's not. It's
not, but it
this.
seems to have the same effect for this state, right?
It's not actually. It's not. The point is this. Uh, so for let me see how I say this. And because
Well, maybe
these
not.
state.
But are you
Yeah, go
trying to
ahead.
say? Let me not call it resolution identities. But are you trying to say that the general thing that works here is when you have that picture with these red boundaries, and you want to glue to another copy with red boundaries, you can just put in the ZZ states there, and that
Yes,
does the.
yes, yes.
Okay, in
You
that
can say
sense,
that.
okay, that I understand. All right, okay.
Yeah, especially I have a diagram. Yeah, I will show you. Actually, there is a crucial difference. There is a CFT. The CFT norm is described by CZ, like Liouville with ZZ boundary conditions.
Hmm.
Yeah. So more specifically, actually, the CFT path integral on the solid torus live on the boundary of this solid torus. It's a torus. So in this metric, it's living at tau goes to plus and minus infinity. That's this gray surface actually on the boundary. And to get a quantum state, you slice it open at the time reflection symmetric slice. So I'm joined here. You slice it open on the boundary. So on the right hand, look at this guy on the right hand side. The quantum state is defined on these blue curves. It's coming from the CFT path integral defined on this gray surface at tau goes to minus infinity. And now the holographic dual of this state is actually coming from the path integral from this gray surface to the red surface. So it's a solid three-dimensional manifold. And that path integral gave you something called Hartle-Hawking state. That state is defined on this red surface. That's the surface for tau goes to tau equal to 0 on this 3D manifold. But now you see the red surface and the bottom gray surface, they actually, if you look at the metric, they have the same conformal geometry, which means they are literally the same up to this factor. So actually, that's the magic here relating the CFT path like path integral to the bulk geometry, and yeah, that's how it works. And just to summarize, actually, what we get is we already see this is the second step. I'm relating the Liouville path integral to this BTZ partition function. And from previous argument, I showed you that these two are the same. So really, these three things are the same. And it's a very general phenomenon. Like more generally, these are the same. Now, so I will just try to, this is the norm. So what about next? I will show the entanglement entropy. So for the entanglement entropy, I will compute entanglement entropy associated to each of the boundary. I will call left boundary A, the other one I will call A complement. So I want to compute the entanglement entropy associated to A. So I first compute the reduced density matrix by tracing out, I give two, a bra and a cat. Tracing over A bar means gluing them together. So for the reduced density matrix, you get a longer cylinder. Where left hand side is the cat, the right hand is the bra. The trace means they glue together. And the replica partition function, you just compute the trace, this guy to the power n. So what you do is you make it longer and longer into n beta. Then the final trace will glue the final A together. So it becomes a cylinder. And the path integral is just given by summing of these characters. So we do the same thing. I do a statistical average. I say instead of evaluating this sum, I replace it by this integral, which is this rho zero formula. So as Gabriel pointed out, this actually can evaluate directly in this case because rho zero is nothing but the modulo S matrix relating identity and heavy states P. And if you do this, actually this gives you the identity block in the dual channel, in the other channel. Like, so what does it mean? Like it's actually very intuitive on this diagram. So our state originally was defined on these blue circles. After you do the trace, you rotate it on a boundary and go back to yourself on this torus boundary. But if you plug in the weight I put here, you will reduce to something that via modular transform, I can think of the states as living on these red circles. So this expression is saying the red circle wind around this torus once and go back to itself. But the red circle is the one that's contractible. The blue one is not. And via this factor is precisely the one connecting the non-contractible cycle and the contractible cycle. So what this says is that actually the dual box solution is one that has a contractible cycle where this blue states actually propagate. And this is actually a very general phenomenon for all the, at least the cases we study, for giving the holographic entropies. You want a direction that's becoming longer and longer, but also contractible in the bulk. That's how you get, even higher dimensions, that's true. And in 3D, 2D, you can realize this explicitly using these CFT data. So now to compute entropy, entanglement entropy is given by this formula. You compute Zn and divide it by Z1 to the n, and you take the log, you take the derivative, and evaluate n equals to 1. As I said, this expression is just the character. The character is known, so you can evaluate it explicitly and see this is the black hole horizon area. But actually, I would do it in a funny way that actually can be generalized to more general situations where the block is not known. So to do that, what we do is now I will evaluate this integral using a saddle point approximation. So to do that, first, these are the PR called Liouville momentum. It's a conventional parameterization of these weights. I will scale it a little bit because that's very common in large C limit. You just get rid of some. You want to get a final answer, so I rescale it a little bit. If I use this rescaled variable gamma, rho zero is given by e to the power of gamma. And this is the familiar Carty formula, actually. And the character actually it's explicitly the expression. Oh, sorry, I forgot to use the cursor. The character is actually you can compute it. It's given by this expression. But I will, instead of using explicit expression, I will write it as e to the c over 6 times the function f. Okay, and so now the saddle point equation is just saying that I want the exponent to be evaluated on a saddle point. So I take derivative and I combine these two together. Then this is the saddle point equation. Okay, and it gave me the saddle point gamma star. Now I plug in this gamma star into my exponent. This is the saddle point value of this integral. Now, when you get this, I plug in the definition of this entanglement entropy. You see, actually, you do some manipulation. You get three terms. So there is first this term. This gives you the saddle point on one like Z1. There is a second equation and third equation, but both of them are zero. The reason is because for the second equation, it is zero because the thing in the bracket is precisely the saddle point equation for the nth replica. The second term is zero because f is linear in n. And why that is true? Because remember the f is just the coming from the path integral in CFT. And CFT path integral has the property that if everything is the same, then when you evaluate the path integral longer and longer, it actually grows linear in n. So the second equation is also zero. It means that the entropy is only coming from the first term, which is given by the Liouville, the saddle point in on first in Z1 star. But Z1 star is the norm, so it is the saddle point on Liouville solution. Liouville is giving you the hyperbolic solution, so this gives you the length in hyperbolic metric. And this is for a chiral answer. If you give me both chiral and anti-chiral, you get an extra factor of 2. And this expression is precisely the geodesic length on this hyperbolic solution. So you see, this is why our formula is true. This is kind of trivial, like because we know, like for the two, this is essentially just rephrasing the Sommerfeld double story, but you'll see it actually generalized doing it this way.
Before
And
you go on, can you
yeah,
comment on whether this is the same as this calculation that Jennifer Lin did, which I also kind of
yeah.
repackaged? Because what I feel like is there's some weird difference in the channel, because you said that in your way of thinking, the direction that gets long is contractible in the bulk, right?
Yes.
I was thinking in the opposite, that the short direction was contractible because you want the temperature in the normal duality, you want the temperature circle to be contractible. And the temperature circle should be getting small at high
Yes.
temperature. But you're saying the
Yes.
long direction is contractible, right?
Actually, it's these two are the same thing. Like it is the like first there is a difference here because here this is really two-sided case. I'm not talking about interval. That's the thing we will talk about just in a minute. On the other hand, I think you're thinking of this like Ishibashi propagate to the other side stuff, right?
Yeah.
Indeed, it is that. Like the reason, like indeed, like the direction that get like go to n like times is this direction. But the fact that it's long
Oh,
is not
okay.
because, yeah, it's not because it's getting replicated to the nth power
Yeah,
making it long, but
it's a UV. Yeah, I see. I get it. Okay. Yes.
yeah, yeah,
Okay.
yeah. We'll really come to the interval case. That is the calculation you did, and also Jennifer Lin did. Yeah.
Okay. I see.
So there's one thing that's crucial. Actually, I think I learned it from discussion with Gabriel earlier. It's very important that this rho zero factor is not replicated to the nth power. Because if that is, you can do the computation, you see everything get raised to its nth power. It gives you zero entropy if you do the saddle point computation. It's very important that this factor only appears once. It doesn't go to its nth power. And that's actually a topological constraint because this factor is making sure that this path integral can give you a contractible cycle in the bulk. And that indeed is coming from, in 2D CFT, you can phrase it in terms of these modular data. And I want to emphasize again, holographic entropies are always coming from some direction that's becoming longer and contractible in the bulk. I really don't have much time. So in the end, if you just ask me if you're curious. Like this allows you to rewrite it as in this edge mode or area operator form. So yeah, I will just skip it for now. So let's really see this line of logic actually generalized to multi-boundary black holes. So to do this, let me show you an example. This is an example with 3 boundaries and 1 genus. So I will call these yeah, let me use the cursor. So I will call these 3, 1. So these to describe these states, actually, you can use the pair of pens decomposition. Just decompose these, like cut these guys here, and 1, 2, yeah. And so using these, I will represent these pair of pens using these lines. That's very common in CFT literature. So you can write this down, this state explicitly down using the so-called OPE block. It's invented by in this paper and recently also used by Chandra and Hartman. I'm actually borrowing their notation using arrows to denote that there's a state defined here. So especially for this quantum state, you have 3 pair of pens. 3 of them. Probably don't even joyride. So 1, 2, 3. Did I miss one of them? Yeah. Anyway, like there are 3 of them. Just trust me. Cannot do it in real time. So, yeah, you do a pair of pairs decomposition. That's the stuff you get. You get 3 OPE coefficients and this block. People call this OPE block. And there are like on each of these arrows, there is a state, the CFT state. And I only use primaries. The descendants are already packaged into this OPE block. And OPE block is just actually half of the conformal block. What do I mean? you can compute the norm. The norm give you another copy and then glue these states together. So when you glue, you identify them. So finally, you get this right-hand side expression. You get 6 OP coefficients and a conformal block. Now, to compute it, really, it seems hopeless to compute this because OP coefficients, we don't know the OP coefficients of holographic CFTs. But the idea is the same. Previously, we average over the spectrum. Now let's average over OP coefficients. So we use the coarse-grained OP data, which is these OP coefficients. And that's really where the eigenstate thermalization hypothesis come from. Eigenstate thermalization hypothesis is saying that the matrix elements between the heavy states is given by this. There's a microcanonical one-point function and a piece that's describing the correction to that. And the point is that this Rij is a random matrix. That's the essence of the eigenstate thermalization hypothesis. And in CFT, first of all, you see this guy is nothing, an element, if I choose the primary, this is nothing but the OP coefficient. I call CIOJ. And secondly, in 2D, this figure disappeared. But in 2D, this first factor, the microcanonical one-point function is 0 because in 2D it's very special. You conformally map it to actually to the plane. So this is vanishing. So in 2D, it's actually telling you these 3-point functions are just random variables. And especially we generalize it a little bit following first proposed by these papers. Actually, I'm relating a lot of them. You generalize it a little bit by saying not only when I and J are heavy, when at least one of them are heavy, this is a random variable. So you propose the OP coefficient itself is a random tensor, actually. So recently, Gabriel wrote a nice paper about it. And as a random tensor, they are specified by their moments. A leading order, it's specified by the Gaussian moment, which is the 2-point function of these guys. And they are fixed by conformal bootstrap again. So they are fixed to be, what do I mean? I mean, the Gaussian moment is fixed to be these functions, which I call C0. More specifically, I'm showing it here, it's given by the DOZ formula divided by some square root of the Carty density of state. Usually people think it's not important, but I will show you actually it's very important that it take this form. So now let's just try to do the average. So when you do the average, this horrible expression, you don't need to know much. I just want to show you because previously you see there are how do you do the average? So this norm computation is reflection symmetric. So I will contract the OP coefficients, for example, living here and here. What it does, because of the Gaussian average, it will identify this M and N. And similarly, for example, if you look at this and this, it will identify the P and the S, P and R and Q and S. So that's exactly what's happening here. You see, it becomes symmetric, and you plug in those factors. Like, okay, density of state, you plug in a rho 0. Each pair of OP coefficients, you put in a C0. Okay, yeah, that just gave you a flavor how to do these computations because I think Gabriel told me he is interested. So now, what's special about it? Let's really plug in the expression for it. C0 is related to DOZ formula divided by these factors. Okay, you do some algebra, many of the factors cancel out. More importantly, for these ones living on this reflection symmetric slice, the I, J, and K labels, when you do this simplification, you see there are some rho 0 factors left. And it's not rho 0, it's square root rho 0. And that's precisely what ZZ boundary condition does. On the other hand, if you look at the internal leg, because internal legs like this M leg both appear in this IJ vertex and PQ vertex, so the square root rho factor appear twice, so they get completely canceled. So the internal legs actually get only left with the Liouville's DOZZ formula. So finally, what you get is for external legs, you get ZZ boundary condition. For internal ones, you get a Liouville OP coefficient. And this expression precisely is a Liouville path integral with ZZ boundary conditions living on the right. So you don't like in the norm computation, you do a reflection, you glue it to its mirror copy. You're doing the average, you only get one copy, and you have these DZ boundary conditions. So you might ask how is it possible? So if you know, you don't need to know the details now, but if you want a better answer, it's because actually when you impose a conformal boundary condition, there's this doubling trick. It's the doubling trick that's giving you the other half of the computation in the norm. And when you write it down, it precisely work out. So actually, it's generally true that you can show the norm of these quantum states is given by the Liouville path integral on the same manifold with ZZ boundary conditions. Okay, so first of all, that's what you see. Secondly, we'll see the same mechanism actually give you the connection to gravity. So because for Liouville, Liouville give you a solution to the Liouville equation with ZZ boundary conditions, which is set. That's what we get here. And that solution, if you plug into this ansatz, actually give a solution for the 3D Einstein-Hilbert action. And when you do the gravity computation on this around this solution, actually it gives you exact quantization of the gravity path integral, and that's equal to the Liouville path integral square, which means that these three things are exactly the same. The average CFT norm is the same as the Liouville path integral with ZZ boundary conditions, is the same as the gravitational path integral from the hyperbolic slicing. Okay, so first of all, you see average actually already give you the norm. Next, let's talk about entanglement entropy. For entanglement entropy, I look at the simplest state. So why didn't I do that previously? Because I want to show some internal legs. These ones only have external ones, I and j. So yeah, this one is simpler. So if I look at this manifold, the entanglement entropy associated to the subregion A is given by the area of this length or the sum over these two lengths. Okay, the homology homology condition tells you have to pick both and pick the minimum of the two. And we will see both where the area and the homology constraint come. So first of all, the reduced density matrix is coming from tracing over BC. When you do that in CFT language, I'm just gluing to another copy along this BC, these two edges. I'm calling M and N. And there are two OP coefficients. This is the reduced density matrix. So the replica precision function, yeah.
Before you go on, could you just make sure that I'm with you on the geometry? So the thing you drew there, the paratangent to the cap, is that supposed to be a bulk slice?
No. Here everything is CFT. I'm doing this.
Okay, so I'm just confused because you didn't show when you mentioned this area MOLA LBLC. It looks like that's a bulk. That's a bulk.
Good. It's the same. Really, this fact. On this metric, CFT live on the tau goes to minus infinity slice, and gravity live the Cauchy slice live on tau equal to 0. These two have the same geometry. So you can either
so
talk
you were
about
showing that. Okay, I see. You're trying to relate.
That's why I say it's emergent. It's not set. It will pop out. So first, you can think of this as this is both the manifold preparing the CFT quantum state, and after you do the average, it will become the Cauchy slice at tau to 0 in gravity.
Okay.
Yes. So the replica partition function just replicate n times, and the trace finally will glue it into cyclic gluing, making it both I. Now, really, the mechanism is the same. How to get RT? I just do the Gaussian contractions. Instead of only the average over the density, I also average over OP coefficients. But in this case, you see the dominant contribution, there are two ways to actually perform the Gaussian contraction. You either do it within all of these red boxes, or you do it within these blue boxes. They are both symmetric. You can both do Gaussian contractions within both. And actually, these two are the two ones that give you the two phases of the RT homology conditions. So the first phase, I would do the average. You don't have to understand completely this horrible expression. You only need to know that after the average, you identify all of these I lines, because within a box, this line and this line will, within the box, the average will identify this with that, this with that. That's what Gaussian average does. So you can see that in this expression, really what all of the I's are identified. And that's crucial because we want a direction that's becoming longer and longer. And now for this terrible expression, I can first perform all the ones in the bubbles, like the P, Q, M, N, R, S. You don't need to know the details. That's really the property of this C0 function. But when you do the computation, it finally reduces to this formula. This formula is very simple. You're only left with an I here, and a special conformal block that will look like this. And now you see that there's really a direction for this I leg that's becoming longer and longer. And because there is only one row zero factor, it becomes contractible in the bulk. And furthermore, the CFT computation tells you that the CFT2 computation is giving you handle bodies. So how to read off in the handle bodies, what's important is the contractible directions. And that's indicated by these ones. Okay, the one tells you which direction is shrinkable. So you can actually read off the bulk dual geometry super easily. If you don't know what I'm talking about, it's not so super important. You have to, yeah, you probably have to have some experience to understand the comment on handle body, but that's not important. Now it's really the same thing because you have something of this form. Now, as I said, the f function, now you use the fact that conformal blocks actually exponentiate. I already used that in the torus case, but it's more general fact. Okay, it becomes this function. And for conformal block with an n, actually it grow linearly because it becomes longer and longer. And CFT passing integral tells you that the exponent actually grow linearly. These two facts, if you plug it in, the entanglement entropy computation is almost exactly the same. The only change is this function f. But we don't need to know what it is. We only need to know the fact that first it exponentiate, second the exponential grow linearly n. So that makes sure the second term and third term are cancelled. Finally, we're left with this gamma 1 star, which again is related to the geodesic length in hyperbolic space due to its connection with the Liouville path integral when you have only one copy, okay, the norm computation. So finally, you get this length. So good, that's the first phase. What about the second one? The second one, I will do an average like this, like these boxes. So what it does is actually it identifies these legs and the ones on the bottom. So it's a new contraction channel, new identification. When you do the computation using the properties, you actually get the ones below. Now you see there are two directions becoming longer and contractible in the bulk. That's the p direction and the q direction. So not surprisingly, again, you use the fact that the conformal block exponentiate and it grow linearly in n, you get the saddles of these two guys in the Liouville path integral. And that's again the minimal length geodesic in hyperbolic space. I want to emphasize one thing. These two average patterns for higher n, higher Rennies, they are different. But for n equals to 1, they are literally the same because that's just computing norm, which is just a Liouville with three boundary conditions, with three DZ boundary conditions. So you actually finally you always look at the same geometry on the emergent hyperbolic space, you are just picking up different saddles. Previously, you pick up the saddle on this I leg. Now you pick up the saddle on this m n leg. Okay. So in the CFT ensemble, really, when you average over p coefficients, you have to sum over all different patterns. In this case, the two Gaussian contraction patterns are dominant because they give you least constraints within these integrals. If you use other patterns, you get more delta functions, killing more the integrals. So it gives you a smaller integral, actually. And that's actually deriving the replica symmetry usually assumed in the holographic dual of RT formulas. And we can actually see it from a CFT consideration, which means that actually the replica partition function, the dominant ones, is coming from the sum over these two terms. And when you take the log, actually, you get the smaller one of the two. Let me say it again. This is telling you that the RT phase transition is just coming from switching of Gaussian contraction patterns, which one is dominant. And that's precisely the safety mechanism behind it. And now let's, yeah, sorry.
Ask one question. So are you saying that in a general observable that you're computing, like we discussed, working other people have discussed before, it was important to go beyond the Gaussian ensemble. Are you saying that in the replica trick, because of, I don't know, the n going to one limit or something, that you don't have to worry about, say, the quartic and higher moments?
Yeah, these give you subleading contributions in this phase, in the phase where high temperature black holes dominate.
I see. And can you say again, when you say the two phases in terms of blocks, it's just you're switching to which, are you just trying to find the dominating identity block? Is that the idea?
Yes.
Switching which one? Yeah, okay. That's
and
also
it's realized Yeah, that's right, precisely. People like to talk about in the quotient space, but really in this higher genus one, I don't know how to do that. Also, this is directly working on the replica manifold. Yes, and the average give you the answer to that. Yes.
Okay, all right, thank you.
Yeah. So now it works for general multi-boundary black holes. I guess I have 10 minutes. So there are multiple choices, like for these ones, a lot of them, but really the choice of cycles satisfying the homology constraints. For example, if I want to compute entropy associated to ijk, I get different ones of different cuts that satisfy the homology constraint. I can get legs, ijk leg, I can get nk leg, I can get pq leg, but all of those choices satisfying the homology constraint exactly separate the diagram into two pieces, and they are symmetric. And when it's symmetric, it allows you to perform the Gaussian contraction. Otherwise, it's impossible because you don't cut your diagram into two pieces. And that's precisely the reason why the one satisfying homology constraint give you dominant contributions and give you the correct Arti formula. Like the leading ones are always coming from this type of uh, configurations. So yeah, good. So all of them work. Um, yeah, I don't. Yeah, I'm really out of time. Let me really be quick. So,
I think
but the mechanism.
maybe don't worry about rushing. So we'll break at the hour mark. But I'm happy to stay and listen to more of this. Just don't feel the need to rush. Yeah.
Okay. Okay. So yeah, first of all, we can generalize this to cases with boundaries. These are so-called BCFTs. The dual of them will be multi-boundary black holes with Carter-Randall brains. So with boundaries, you have to specify boundary conditions. There's a preferred choice of boundary condition called Carty boundary condition, conformal boundary condition, where the conformal symmetry is preserved along this line. When you have a boundary, the states are no longer defined on circles, they are defined on intervals with two boundary conditions. So an example is this BCFT thermal field double state, like this. It's the previous cylinder now really with lines, so it's a cylinder, it's a strip. You can still compute the replica partition function. Again, it's just this thermal field double raised to nth power, you get this expression. You need to notice that there's only one Virasoro symmetry because the boundary condition break half of it. And now I have to average over this row again. So I use the average in the BCFT ensemble. So it's almost giving you the Carty formula, but not quite. There is extra factor called G factor. The G factor is special to BCFTs. And when you do that, the entropy computation, you just do the replica trick, it actually gives you this answer. So let's try to understand what it means. So first of all, in gravity, I have to first find the solution. The solution is again coming from hyperbolic slicing. What you do is you first use the upper half plane. Then you plug in this solution. You see now I do a coordinate transformation. I use relating the cosh and the sign of mu. Then this mu direction becoming this rotation direction from 0 to pi. Okay, and the t equal to 0 slice now lives on in this like vertical direction. Okay, that's the slice we will focus on. And the dual of the Carty boundaries, which are these red and blue ones living on the bottom slice, which is tau goes to plus minus infinity, are the ones actually are the ones that dual to something called Carter-Randall brane extending into the bulk. That's these spherical caps. The G function actually is related to the tension of the branes. So let me just look at the t equal to 0 slice. The slice look like this. So this manifold really has three pieces. There are these spherical regions, the blue lines. This is a strip that's symmetric. And that's the solution with tensionless branes. And that's really just half of a torus. The half is related to the doubling trick in BCFT. So you only keep one copy of it. And that giving you the length between these 2 points in the middle is c pi squared over 3 beta, which is half of the original the cylinder answer. And there are these the fact that these are like the branes with tensions actually change the spheres into spherical caps. So one of them go upper, one of them go lower, but the length between the blue guy and the green guy is precisely log of g. So the total length, the geodesic length, the minimal geodesic length is the sum of the three guys, and that's precisely the entropy of given by the CFT computation. Matches
I'm
with
sorry,
the geodesic.
which colors are the brains in this picture? Which lines are the brains?
Yeah, the branes are
Those
the red and green.
The red and green. So the bulk
Yes.
region is the middle region, the bulk region, is that right? Are you thinking of, I'm also a little confused. Are we looking at a bulk picture or is this still a boundary picture?
Now it's a bulk picture. Like the boundary is
Now it's a
living on
bulk.
this. Yes, this is the t equal to 0 slice. This is where you compute the RT formula.
Okay, good. Okay, thank you.
Yes. Yeah, in the CFT, it's just this. Yeah, I should probably draw it better. It's the one on the bottom right. That's where you get the quantum state.
Mm.
Yeah, that matches. And actually, let's look at a more interesting example. Now using the OP coefficients, just look at this three interval example. That's a three entangled states. That's very similar to the previous, like the three pair of pants case. Now this is an open pair of pants because you have boundary conditions, blue, green, and red. Sorry, green, red, and brown. The replica partition function can be computed this way. There are two differences with the previous case. First of all, I don't have the norm square because I only have one Virasoro symmetry. Secondly, there is this factor GAGBG square. That's normalization in BCFT. You might think it's not important, but actually it is. It will tell you the topology. Now to compute it, again, I use the ensemble average of BCFT OP coefficients. Again, this is determined by BCFT bootstrap. So it's determined by this. There are these Gaussian factors. The dependence on boundary conditions factor out. So the dependence is only coming from the primary labels. So it actually becomes exactly half of the CFT answer. The boundary conditions all factor out. It's kind of magical. Like in the usual BCFT, it's not true, but after the average, it is true. They factor out. So again, I don't need to show the details. You just get these expressions from the BCFT computation up to the prefactors. This is precisely the old answer. You take the log, you get the second factors. And these G factors, actually, if you plug in the replica trick, you get the log G. So finally, exactly, you get the correct RT formula in this case. So what are actually these prefactors doing? You might think they are not important. They are actually important because now I will show you, they actually tell you the topology of the bulk solution. More importantly, in B8S3 BCFT2, the contribution from the brain is giving you the G factor to the Euler character of the brain topology. For the first phase, for example, the difference is in the C brains. C brains are the red ones. G to the n means that the dual of these, the brains actually have topologies of n disks, and that's indicated by these guys, these regions, these what color? What do you call it? Orange-ish color. And you see there are D disks. On the other hand, for the second phase, you get 2 minus n. What is 2 minus n? It's telling you in the bulk solution, all of these branes are actually connected. And that's precisely the Euler character of this brane. And that actually telling you it's a replica wormhole. And more importantly, actually, I will show you if I have time, that this is really, if you properly set up the question, it's pointed out actually by some papers, including one of the House paper, that this is a replica wormhole computation. So actually, this is also telling you that the CFT computation gave you a replica wormhole, explaining some of the other RT phases comparing to the Hawking one. Let me see how much time I have. Let me first finish this stuff. So we have another building block, really combining the CFT and BCFT that involve another OP coefficient. You can do it. It also gives you the RT formula in that case. In the most general situation, you can just use the CFT1, BCFT1, and the one connecting the two. That actually gives all the RT formulas like for these type of states and the bulk duals. Okay, I'll wrap up in 3 minutes. Yeah, sorry.
Okay, yeah. If you can wrap, I think, yeah, if you can wrap it in a few minutes and then we can break and then I can continue with you. Yeah, that would be great.
Sure. So these are black holes. You might think they're very special. Actually, they are not. The derivation can be generalized to provide a derivation for the entanglement in the vacuum state. So that actually, Gabriel also have a paper. It's first pointed out by this Omori Tachikawa paper that when we do entanglement entropy computation, even for intervals on vacuum state, I can use conformal boundaries to regulate the computation. So that means that you put conformal Cardi boundaries with a very tiny size. You just need to shrink the size in the end. That gave you interval entanglement entropy. But for this computation, you can conformally map exactly to the previous thermal field double state set up. And if you do this, you will see the single interval modular Hamiltonian is precisely the BCFT Hamiltonian. When you take the small hole size limit, it actually is giving you the heavy state in open channel. That's what Gabriel was pointing out. It's a very long cylinder. You replicate in the in this this open channel direction, but really the long direction is in the closed channel, and that gave you the correct RT formula. But we already know this case is single interval is universal, so the non-universal one actually just coming from more you give more triangles. Like for example, this case, if you want to compute the entanglement entropy of A1, A2, I triangulated my manifold into two triangles and use the average of BCFT OP coefficients. You precisely get two faces. The two faces give you the RT formula for the red curve and the blue curve. That come from the Z2 quotient of the black hole, actually. So we're actually getting a new derivation of the multi-interval entanglement entropy from this BCFT ensemble, coming from the universal statistics of heavy state in the BCFT. Okay. Yeah, I will not comment more on this. We can discuss more. And this actually gives you the holographic tensor network. It tells you that the holographic tensor network is coming from triangulating the CFT path integral and use BCFT data. Especially the random tensor network is coming from using the ensemble average of BCFT coefficients. Yeah, that's what I'm saying here. And the connection to geometry, it looks like you're doing CFT path integral, but really, as Gabriel pointed out, to see the geometry, you don't directly do it on the Cauchy slice. It emerges from the hyperbolic slicing and connecting the CFT path integral to the bulk Cauchy slice. This makes the tensor network beyond toy models. Really, it avoids all of the problems previously people found. Like we get areas, we get non-Renyi flat Renyi spectrum, we get superposition of geometries, we get the correct RT formula, the correct phases. And I want to point out this line of logic, we recently not only use it to describe quantum states, but also we describe partition function. That in those cases, it seems that there are exact spacetime tensor numbers for partition functions, and there is a nice connection to generalized symmetries. You can read our other papers. I don't have time to explain it, but just telling you that actually you can see some properties previously proposed for random tensor networks and perfect tensor networks actually have their origin in CFT path integral. Yeah, I'll explain it later when you have time. Also, this setup, if you set up carefully, actually it does explain, it is giving you some replica wormholes in the context of black hole information paradox. That's one, the so-called East Coast model. There's a black hole region and there's a bath region. If you set up carefully, looking at the bath itself described by a holographic CFT, then the entropy computation is precisely given by one of the three interval computation after you do the conformal transformation. And the two phases, like giving you the Hawking phase and the replica wormhole phase, is precisely given by the switch of dominance of the two Gaussian contractions. So the phase transition is coming from different ensemble average patterns of OP coefficients. And this is one example we show in our paper that it's a very general phenomenon in almost all replica wormhole models. Okay, so yeah, I'm running out of time, so let me just recap. So to conclude, we propose that the StatMech be connecting the CFT path integral and the emergent semi-classical gravity is this statistical average over OP data. And in the closed case, you get these answers. In the open case, you get you get this connection. And finally, two applications are: first, you get a new derivation of entanglement entropy in vacuum state, and you get the holographic tensor network really from the BCFT Legos, and you can apply it to replica wormholes. I also have some. We also have some follow-ups, for example, the reflective entropy, whatever. But I really don't have time to explain. And with that, I will thank you for your attention. I guess.
Okay, thank you very much, Yikun. Very nice talk. I have many questions, but before I ask any of them, does anyone else want to ask a question? Anyone from the Zoom audience here? Okay. Okay, if not, so I think that I'm still a little bit struggling to understand the relevance of Liouville in this story as compared to Liouville in Virasoro TQFT. I realize that you're thinking from the boundary point of view, so maybe there's a slight difference, but in Virasoro TQFT, there's supposed to be, in that case, you're starting with a bulk. You're starting with 3D gravity. And then when you put it on some wormhole topologies, you get the Liouville partition function. Earlier you had a description of partition functions of 3D gravity on handle bodies, right?
Yeah.
And you said those are also produced by Liouville ZZ states.
No. Only the one with one copy. The norm is related to the Liouville with the boundary condition.
Isn't a so if you have a maybe I guess not every handle body is a norm, but some handle bodies can be computed as a norm, right?
Yes.
Those can also be computed using the ZZ boundary state or no?
If you more specifically in the replica partition function, when n is 1 and 2, you can do it that way. The other ones really it is a Virasoro TQFT computation with boundary conditions.
I see. I'm just wondering what is the so is the way that Liouville is popping up in your story just entirely different than the way Liouville comes up in Virasoro TQFT, or are they related?
It's related but different. Really, I'm thinking of it as you have a microscopic CFT that's not related to Liouville at all. Okay. Then you do the average. The average answer is Liouville.
Okay. That makes sense. Oh, let me actually stop the recording here.